this chapter, we will be looking at concepts in probability. In this lesson, we will be discussing mutually exclusive and non-mutually exclusive events.
All right, well, before we get into the lesson here, which is about mutually exclusive events, just a little bit of a review here. So complement, and remember this is coming from set theory, but it has its place here in probability as well. The complement of an event is, so the complement of an event A is the event A not occurring, right? And we denote that with a bar over top. Now in set theory we used a little apostrophe. They mean the same thing. In this context here, in the context of set theory, when we had A plus A naught, the result was the universal set. In this case right here, when we're talking about probabilities, the probability of A plus the probability of not A, okay, its complement is going to be 100%. And we would denote that like this, okay? And again, you're seeing the overlap here with set theory using a Venn diagram. So this represents the set of possible or successful outcomes in an experiment, and out here this is the unsuccessful ones, and together that's the whole universe, and away we go. A and B, okay, so the event of both A and B occurring together simultaneously, we denote that A and B, okay, and you're going to see this becomes important in probability, okay, when two events overlap. Now they look like this, right, in the Venn diagram, where this represents, okay, a randomly chosen object, okay, that is part of both sets at the same time. Compare that with A or B, and really in this case right here we're really looking at the vocabulary here. A or B is the event where an object is either in set A or in set B, not necessarily in both, although it could be in both, okay, but it's in one or the other or both here, and that's denoted like this. That is our union. So here's set A, here's set B. There's the union between the two of them. And again, that becomes important in probability as well when we start discussing different kinds of events here. Now, that's our lead-in to this idea of mutually exclusive events. Now, when we start talking about mutually exclusive events, it should be noted here that we are specifically talking about or situations, okay? Or, where we're looking at an event or an outcome that could be in one set or another. It could happen one way or another, and we're okay with both of those. But that's the sort of scenario we're looking at here. Now, when two events are mutually exclusive, okay, they cannot occur at the same time. That really, got to emphasize that they cannot occur at the same time, okay, and are said to be, if you're talking about sets, if we were talking about sets here, they would be disjoint sets. The outcomes, the specific things that we're looking for are coming from two disjoint sets. There's no overlap. They mutually exclude each other is the way you want to think about it, okay? So for example, in this case right here, whatever this set is, A, it is excluding B, just like B is excluding A. There's nothing that is of overlap between them. Now, but remember, we're talking about or events. It could happen this way or this way. What we're trying to say here is that if they're mutually exclusive, it's not possible for them both to occur at the same time. It is not possible that they're in both sets. So this is what we're talking about here. Here's a situation where we might have an or event, but it is possible, okay, it is possible to pick an outcome that is in both of those sets. Over here, this is also, I'm shading in A or B. Okay, I just shaded in A or B. But in this case here, it is not possible that the object that I pick could come from both sets, so we call those mutually exclusive. Now, mathematically, okay, in terms of our formulas here, let's zoom in on this. The probability that A or B occurs if they're mutually exclusive, okay, this is for mutually exclusive events, is the probability that A occurs plus the probability that B occurs, okay? The probability, and then, sorry, the other way of writing it, if you want to think of it like this, is instead of writing the or, I could write the union symbol. It means the same thing. You'll notice the result here is identical. The probability of A and B, okay, okay, happening at the same time is what we're referring to here, is the empty set. That is not possible, okay? You cannot have them because they are mutually exclusive. There is no overlap. So, whoops, wrong way. Now let's take a look at an example here real quick. So in this case right here, if each of the 13 outcomes in a sample space is equally likely, then find the probabilities. Let's take a quick look here. So each one of these little dots here, okay, refers to an outcome, a specific outcome here, and then these sets are referring to the events. So events A and B are mutually exclusive because there is no overlapping, okay, and therefore the probability of A and B is 0. Okay, so this is the test for mutually exclusive. Okay, if the probability that A and B occur together is 0, then those two sets are mutually exclusive. Let's take a quick look here. Okay, now what's the probability of event A given this diagram? Well, there are 4 positive outcomes out of 13. What's the probability of B? There are 3 outcomes out of 13. So now the probability of A or B, there's 4 here and 3 here. So one way I can do it is just to count that out. That is going to be 7 out of 13. The other way I can think about this is that it's going to be the probability of A plus the probability of B. That is 4 over 13 plus 3 out of 13, which is the long way around, 7 out of 13. But like I said, I could have just counted that out. Okay, could have just counted that out immediately. P, the probability of A and B, that is the empty set. That is 0. Okay, sorry, I shouldn't write it like that. It's not that the probability is the empty set. Actually, I should come up here. It's not that the probability is the empty set. The probability is 0. A intersect B is the empty set. Okay, but the probability is not the empty set. So here the probability is 0 because there are no elements that are in both. And that's what was stated right there. Now, let's take a look at non-mutually exclusive events, okay? Because you really can't talk about mutually exclusive without also talking about the opposite here, non-mutually exclusive. And these are simply events that do have some common outcomes. Even if it's just one, that's enough for them to be non-mutually exclusive. So right here, okay, if I was to shade, let's do it over here. Okay, what they're trying to show you here, okay, is that there's some overlap here, but I can do this. I don't want to talk to you guys about it this way. If I now shade A or B, okay, I shade A, but at that point right now, even the process of shading A has caused me to shade over some of B. So now shading both of those, okay, is going to look like this. There is some overlap between them. So there's a spot here, there's a subset that's common to both. Now, watch this. I'm going to do this again because I think this really does illustrate the formula quite nicely here. So this is what I'm going to do here. Here's A, here's B. I'm going to do this again. I am going to shade A or B. Now think back to set theory when I did the shading back there, if you had watched that video before. When you shade union, you shade this set and you shade this set. Okay? You shade them both. Now watch this. I'm going to shade set A. Okay, now I'm going to do this going the other way here. Now I'm going to shade set B, and I'm going to do it this way. Now notice what I did. Notice that this section in between was covered twice. Okay, because it's overlapping. So if I shade A, shade B, I'm going to cover this little spot here twice. Now, that leads us to this formula right here. If I've got non-mutually exclusive events, then the probability that A or B occurs is going to be the probability of A plus the probability of B. But by the time you've added those two together, that overlapping part here, you've counted twice. Okay, you counted it when you counted A, you counted it when you counted B. So what we're going to do here is we're going to subtract that probability just once. And if you subtract it just once, you clean that up. Okay, so here, same thing. This is just in terms of the notation. So the probability of A union B is going to be the probability of A plus the probability of B minus, okay, the intersection between those two. So you got two formulas that you need to be familiar with. The formula for non-mutually exclusive events, and then over here, the formula for mutually exclusive events. So now we're going to take a look at some problems where we're going to have to make decisions between which one that we're looking at here before we can make the calculations.
If each of the 13 outcomes in the sample space is equally likely, find the following probabilities.
Okay, so in this case right here, the question that we're looking at here is referring to this diagram. Okay, so maybe we'll zoom out here just a little bit. So events A and B are not mutually exclusive because we can see that there's a bit of overlap in between them. Just the one, but that's enough to be non-mutually exclusive. So the probability of randomly picking something from A, now there are 13 here that we're told about, is going to be 4 out of 13. Okay, because there are 4 dots in the A set, in the A circle. Granted, there are 2 subsets here, but we count them all. The probability of being in B is 5 out of 13. And that's just, again, just a matter of counting all of the dots that show up inside the B set, which is that circle. And again, there are 2 subsets there, but you count them both. Now, A or B, and I'm going to do this 2 different ways here, but I can just count this out here. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 out of 13. I know it's going to work like that. The other way of doing this, to get that 8 out of 13, would be to take the probability of A, okay, the probability of A, add the probability of B, and then subtract the probability of A and B. Okay, that is going to be 4/13 plus 5/13. Now look at that. 4/13 plus 5/13, let's zoom in on that, is going to be 9/13, which is not quite correct. But what's the probability of A and B? How many are in both? Well, just 1. So 1 out of 13. So 4/13 plus 5/13 minus 1/13 is going to be, there's the 8/13 that I'm looking for. So 2 different ways of doing it. I can either count it out here or use my formula. And again, in this case right here, I probably even should have put this thing up here, but that's okay. Probability of A and B we saw here was just going to be 1 out of 13. The overlap between the 2.
Classify each of the following events as either mutually exclusive or not mutually exclusive.
Okay, so let's take a look at this first one here. It says a card is drawn from a standard deck. Okay, so the event is that the card is, we got a face card is selected, a diamond is selected. Okay, now the question is it possible for a card to be both a face card and a diamond? And the answer is yes, it can be both. So these are not mutually exclusive. Okay, it is possible to be for an item to overlap both those sets. Let's look at the next one. 2 dice are thrown. The dice both show the same value, is event A. The dice show a total score of 8. Okay, is it possible that there is a result that has it such that the both dice are the same, and at the same time the score is still 8? And the answer is yes. It could be a 4 and a 4 that I've rolled. So these do have overlap, so they are not mutually exclusive. Okay, 2 dice are thrown. The first event here is that the dice both show the same value. Okay, so similar to the one that we just did. The total score is 9. Is it possible that I could have an event where both dice are the same and at the same time the total score is 9? And the answer is no, that's not possible. So these 2 sets here are in fact mutually exclusive because they don't have any overlap, they exclude each other. If I've got something out of this set here, it is not possible for it to have this one, so it excludes this possibility. That's how you want to think that one through.
Determine whether the following events A and B are mutually exclusive.
All right, so now to figure out whether these are mutually exclusive or not, we got to do a little bit of math here, okay? Now, let's just take a quick look at these things here. The probability that A occurs is 1/8, the probability that B occurs is 2/5, the probability that A and B occur is 0. That's the key here. So this right here is definitely mutually exclusive, okay? Because the probability that they both occur together is 0. Now look over here. The probability that A occurs is 2/5, The probability that B occurs is 1/5. The probability that A or B occurs is 3/5. Now that isn't quite enough for me to be able to tell by looking at it. So what I'm going to do here is to test it. I'm going to figure this out here. So the probability of A or B should be the probability of A plus the probability of B. Now, this is true if they're mutually exclusive. If they're mutually exclusive, that's what it should look like here. So the probability of A or B was 3/5. The probability of A is 2/5. The probability of B is 1/5. And that is in fact 3/5. So that is a true statement here. So that means these are in fact mutually exclusive. So that is correct. Okay? Now compare that to this one down here. The probability of A is 0.3, the probability of B is 0.4, the probability of A or B is 0.6. So again, for me to test this, I'm going to see if it satisfies the equation that I know is true about mutually exclusive events. So A or B is 0.6, probability of A is 0.3, the probability of B is 0.4. Now, that's 0.7. They are not equal to each other, so that means this can't be mutually exclusive. This is not mutually exclusive, okay, because those two should have been equal to each other if this scenario here really did describe mutually exclusive events.
Use the following information to determine the probability of the given event.
Okay, so just given the information that we've got here, we're going to figure out some of these probabilities. So probability of A is 3/5, probability of B is 1/3. We're told that they are mutually exclusive, and now we're supposed to calculate the probability of A or B. Okay, well, the probability of A or B, if they're mutually exclusive, will be the probability of A plus the probability of B. That is going to end up being 3/5 plus 1/3. There's nothing else to include here because they're mutually exclusive. Now, this is going to require me to convert these to a common denominator, which is going to be 15. So this is going to end up being 9/15 plus 5/15. Sorry. Yeah. Is that right? 9/15 plus 5/15. Yeah. So 14/15 altogether. Sorry, for just a quick second there, I did that math wrong in my head. Actually, it doesn't look right the way I wrote it. Do that better. So this will equal 14/15. Okay, good. Now, look at this next one. The probability that A occurs is 0.4. The probability that B occurs is 0.3. Now, we're told that the probability that A or B occurs is 0.65, and we want to calculate the probability of A and B. Now, this sort of implies that we might be looking at non-mutually exclusive events here, but let's check this out here. We'll assume that that's the case here. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now this is really what we're looking for here, but we'll fill stuff in. So this is going to be 0.65, 0.4 plus 0.3, and then this is the probability. We're going to subtract the probability of A and B. Okay, well, 0.65, that's going to be 0.7 when I add that all up. Whoops, wow, I don't know why I wrote it like that. That's so weird. A and B. Now I'm going to bring this probability of A and B over here, and I'll subtract the 0.65 and bring it over here. So the probability of A and B is going to be 0.7 minus 0.65. So close, but there is a little bit of overlap there. There's really like a 5% chance that you're going to get A and B, but there's still a possibility, and so we know that these are in fact non-mutually exclusive. Let's look at this last one here. The probability of A is 0.4, the probability of B is 0.2, the probability of A and B is 0.15, and now we're going to calculate A or B. And again, these look like, well, these are non-mutually exclusive events because the probability of A and B isn't zero. So A or B, probability of A or B will be the probability of A plus the probability of B minus the probability of A and B. So the probability of A is 0.4, probability of B is 0.2, and the probability of A and B is 0.15. So that's going to be 0.6 minus 0.15. So the answer is the probability that A or B occurs is going to be 0.45.
There are 30 students in a class. 16 students are taking chemistry and 21 students are taking biology. Of these students, 12 students take both. What is the probability that a randomly selected student in these classes take chemistry or biology?
Okay, so we already know that these are not mutually exclusive here. So now the question is, what is the probability that a randomly selected student in the class takes chemistry or biology? So this is the probability of chemistry or biology, okay? So this will be the probability of chemistry plus the probability of biology, and then we're going to have to subtract the probability of chemistry and biology. Well, the probability of taking chemistry is going to be 16 out of 30. Now, granted, I can reduce that at this point in time, but I'm not going to reduce it. And the reason I'm not going to reduce it here is because I'm going to end up with a bunch of fractions here that are all out of 30 here, and they already have common denominators, so I might as well not do that. The next one here, biology, is going to be 21 out of 30. And then 12 students take both, and so that's going to end up being 12 out of 30 right there. Okay. Now, again, if I had simplified that as I went, then I wouldn't have these things just as beautifully set up as they are right now. Okay. Because all I have to do now is add the numerators here. So 16 and 21 minus 12, put that all together, and you're going to get 25 out of 30. And now I can reduce that because they're both divisible by 5 there, so probability is 5 out of 6. Now that's using the formula here, but I could also use the Venn diagram. Okay, I know that there are 30 in the universe. Okay, and that this is, let's say that this is chemistry and this is biology here. Now, in order for me to understand this, I gotta fill it in here, and I gotta start from the center here. There are 12 students in the overlap. I know that there are 16 students total in chemistry here. So if there are 12 in this subset of chemistry, there's got to be 4 out here. If there are 21 students in biology, and I've got 12 here, that means there's got to be 9 right here. Okay? Now, what's the union of those two sets? Well, 4 and 12 is already 16, plus that 9 is 25. So I know that the probability of chemistry union biology here together will again get me 25 out of a total of 30 that's in the universe. And again, I can simplify that to get 5 out of 6.
One card is drawn from a deck of 52 cards. Determine the probability of the following.
Okay, so here we're figure out the probability that the card is either a spade or red. Okay, so that's going to be the probability of getting a spade or, which is the union symbol, red here. And there's a couple different ways we can do this, but let's stick with our plan here, our formula. So this will be the probability of getting a spade plus the probability of getting a red minus the probability of being a spade and red. Okay, well, the probability of getting a spade, okay, is going to be, and I'm going to do this in terms of the overall number of cards here. So there are 13 spades out of the 52 cards. The probability of getting a red card, well, let's see, diamonds are red, hearts are red. So that's going to be 26 cards out of 52. And then over here, well, there are no red spades. Okay, there's no card that fits into both of those categories simultaneously. So that's 0 out of 52. So these are mutually exclusive sets here. And when you add those together, the 13 plus the 26, we're going to get 39 out of 52. And now the interesting thing is when you divide that out here, basically this is going to reduce down to 3/4. Okay, so the probability is 0.75 or 3/4 that you're going to get a spade or a red. Now let's take a look at this next one here. What about getting a spade or the card is a face card? Okay, so the probability of a spade or a face card. And again, we're going to use the formula, the probability of getting a spade plus the probability of getting a face card minus the probability of getting a spade and a face card. And again, I'm going to work with these fractions here out of 52 here. So there are 13 spades out of 52. Now, how many face cards are there? Well, there are 4 suits and 3 different face cards from each. That's 12. Okay, so it's going to be 12 different face cards there, and I'm going to subtract. Okay, now what's the probability that you've got a spade and a face card? So together, it's kind of simultaneously there. Well, how many spades are face cards? Well, 3. The jack of spades, the queen of spades, and the king of spades here. So that's 3 out of 52. So now I've got 13 plus 12 minus 3, all out of 52. And that becomes 28 out of 52 here. Now, if we try to simplify that, see what kind of fraction we get, there's really not much we can do other than, well, they're both divisible by 4, so that gets me 7 out of 13. That's about as simple as that's going to get. That's okay. There's the probability, 7 out of 13. Let's look at this last one here. A red card or a black queen. Okay, so the probability of getting a red or a black queen. Okay, and so that's going to be the probability of getting a red plus the probability of getting a black queen. And then we got to subtract the probability that it's red and a black queen. And like I did before, I'm going to do these all out of 52 here. So how many red cards are there? Well, half the deck is red, so it's going to be 26 cards out of 52. How many black queens are there? Well, there are only 2 suits that are black, and there's only 1 queen in each of those suits. That's really just 2 out of 52 cards are going to be black queens. And how many of those cards here are red and black queens? Well, none of them. Okay, these are mutually exclusive. There's no overlap between those 2 particular sets here. And so we're going to end up with 28 out of 52, and that's actually the exact same, 28 out of 52, which is the exact same probability we got at the end of the last question, which we saw reduced down to 7 out of 13. Okay? And so there you go.
A single card is drawn from a deck of playing cards. What is the probability of the following?
Okay, so we're looking for here the probability that we got a black ace or a red face card. So the probability of getting a black ace or a red face card. Now that's going to be the probability of getting a black ace plus the probability of getting a red face card minus the probability of getting I'm going to run over to this one, black ace and a red face card. Okay, so probability of getting a black ace. Well, there are 2 suits that are black and an ace in each of those, so it's going to be 2 out of a total of 52 different cards. A red face card. Okay, well, there are 2 suits that are red, and there's 3 face cards per suit. So that's going to be 6 out of 52 cards there. Okay, and how many of those are going to be black aces that are exactly red face cards? The answer is none of them. There's no overlap between these 2 specific sets that we're looking at. They're mutually exclusive. So putting this together, we're going to get 8 out of 52 cards fall into either of those 2 categories. And when you reduce that, they're both divisible by 4 here. We're going to get 2 out of 13 is my probability. Now over here, the probability of a club or a 4, okay, so this is going to be the probability of a club or a 4 will be the probability of a club plus the probability of a 4 minus the probability of getting a club and a 4. So the probability of a club, well, that's 1/4 of the cards are going to be clubs here now, but I'm going to write it out as 13 over 52. And I'm just doing this out of 52, and you've seen me do this for the last little while here, just so that they all have common denominators right from the beginning. That makes the addition and subtraction very easy for me. I just have to deal with the numerators, and then I can simplify later. Okay? How many 4s are there in the deck? Well, there are 4 suits. Each one has a 4, so there's 4 4s. So there's going to be 4 out of 52 there. Okay, and now we've got the club, the probability of getting a club and a 4. Well, is it possible to have a club that is also a 4? And the answer is yes. There's only one card that does that, though, out of all 52. So that's the 4 of clubs. Okay, so now I've got 13 cards here, 4 cards here, but I've added that 4 of clubs twice. So 13 plus 4 is 17, minus 1 is 16 out of 52. And actually each of those is divisible by 4, and if I do that I get 4 out of 13 is the probability of getting a club or a 4.
In a class of 35 students, 25 are taking mathematics, 8 are taking history, and 5 are taking both mathematics and history. If a student is chosen at random from this class, what are the odds in favor of not taking either?
All right. Well, a question like this, now notice what's going on here. You got a lot kind of happening all together here. We're told 35 students in the class, you got 25 taking math, 8 are taking history, 5 are taking both here. As soon as you start giving the information like that, this really kind of screams Venn diagram to help us figure out what's going on here. And I think this is a great tool for use in probability as well. So we've got math, we've got history in our little universe here, or in our sample space, okay, because that would be what we would call that in a probability chapter. We know there's 25 in math and there are 8 in history. Now what's important right now is that there are 5 in both. And so there's the overlap. There's math and history. Now remember, there are 25 in math in this set here, and that consists of 2 subsets. There's already 5 taken into account here, which means there are 20 that are taking just math. In history, there should be a total of 8. There's already 5 in that subset, which means there are 3 here. Now, putting this all together, 20 and 5 and 3, that's 28 students. But in a group of 35, that means that there are 7 out here that aren't in either. So there we go. So now if a student is chosen at random from the class, what are the odds in favor of not taking either? Okay, well, odds in favor of not taking either. Well, first of all, how many are not taking either? 7. And then there are 28 that are taking either math or history. So this is the complement of not taking either, which would be the union of those 2 sets. So there's the odds in favor.
A traffic light on the side of a busy street is green for 25 seconds, yellow for 5 seconds, and red for 30 seconds for every minute during the rush hour traffic from 4 p.m. to 6 p.m. What is the probability that the traffic light will not be green when a motorist first sees it during rush hour traffic?
Okay, well now here's a practical question. So for every minute, okay, it's green for 25 seconds, yellow for 5, and 30 for red. Okay, so then the question is, what is the probability that a traffic light will not be green when a motorist first sees it during the rush hour traffic? Okay, well, so we're assuming there's rush hour between 4 and 6 there, like it says. Okay, so basically the entire 2-hour period here can be modeled by what happens in that 1 minute. And so in this case right here, so the probability that it's going to be not green, okay, is essentially going to be the probability that it's either red or yellow. Okay, so it's the probability. It's going to be the probability of those 2 sets right there, and so that's going to be the probability that it's red plus the probability that it's yellow. Now, I would also include in this the probability that it's red and yellow, but I think it should be pretty clear that that's actually going to be 0. So the probability that it's red here is going to be 30 out of 60 seconds. Probability that it's yellow is going to be 5 out of 60 seconds. Okay, and so putting those together, that's 35 out of 60 seconds. Okay, minus the 0 out of 60 seconds, but there we go, 35 out of 60 seconds here. I don't know, let's divide those both by 5 here. What do we get? We get 7 out of 12. So the probability is 7/12 that when a motorist sees the light for the first time, that it won't be green.
A car manufacturer keeps a database of all the cars that are available for sale to all the dealerships in Western Canada. For Model A, the database reports that 43% have heated seats, 36% have a sunroof, and 49% have neither.
Okay, so the question here says, determine the probability of a Model A car at the dealership having both heated seats and a sunroof. Okay, so let's think about what we know about the way the probability works here. So let's say if we wanted to figure out the probability of heated seats or a sunroof, okay, that would be the probability of heated seats plus the probability of a sunroof minus the probability of heated seats and a sunroof. Now, this is what we're actually looking for in this problem here. So what I'm going to do is I'm just going to manipulate the equation. I'm going to bring this to the left-hand side, and I'll bring this to the right-hand side. So this will be the probability of heated seats and a sunroof is the probability of heated seats plus the probability of a sunroof minus the probability of heated seats or a sunroof. So all I've done is taken this formula that we have for non-mutually exclusive events and switched the position in the formula here. Now, I know that the probability of a heated seat is going to be 0.43, 43%. I know that the probability of a sunroof is 36% or 0.36. Now I'm going to subtract the probability of either. And the thing is, I don't have that. Okay, let's think about it like this. If we take a quick look here, here's the heated seats, here's the sunroof. What I do have is this probability out here at 0.49. The probability out there, okay, in the negation of that set is 0.49. That's what we got here at have neither. Now, but if that's the truth, this is the exact opposite of what I want. Therefore, the probability of having heated seats or a sunroof, the union of those two sets, is going to be 1 minus that, 1 minus 0.49, and then the answer will be 0.51. So down here, I can come down here and say, this must be 0.51. And so now I just go to my calculator, and 0.43 plus 0.36 minus 0.51 is equal to 0.28. So therefore, the probability of having both, okay, is 28%. Now let's take a look at this last one here. It says, what are the odds against heated seats? Against heated seats. Okay, well, what's the probability of having heated seats? That was 43%. Okay, so the probability of having heated seats is going to be 43%. So if we take, well, think about there being like, interpret this in terms of like hundreds here, okay? So let's say we had like 100 cars here, 43% of them would be 43 cars. Those are the heated seats. So against that, that would be 57, okay, to 43. Now, 57, I'm just going to take a quick look here, just take a look and see if there's anything. Yeah, that's as simple as that's going to get here. Okay, so there are your odds against. Remember, against meaning over on this side here, this is the number of possible ways that this could happen without heated seats. This is the number of ways it could happen with heated seats. Actually, it's not exactly the way I meant it. I actually meant success to failure. It's just this one's worded a little differently, so just be careful when you read those questions. Good.